Well, hello everyone. Welcome back to Adrian's Digital Basement. On today's video, we're going to be revisiting the Laser 200, also known as the VZ200, VZ210, and a bunch of other names depending on the market that this computer was sold in. This is going to be part 2 in this series, so I recommend you watch part 1 first because as usual, I'll be continuing off from part 1 and trying to get this machine working. To recap part 1, we took a look at this machine, the specs and the outside and inside of this computer, and I determined that this machine wasn't working. I did a bunch of troubleshooting and concluded the CPU was most likely bad, so I swapped that out, and that didn't make a difference. And then I did some more troubleshooting, and I thought the ROMs were bad, but when I removed the ROMs from the board and we tested them in the Retro Chip Tester Pro, those were fine as well. But in the process of removing the ROMs, I found that there was a broken trace on the back of the motherboard, and this was something that I didn't cause. So I repaired that, put it all back together, and this thing still wasn't working. Even when I tried a dead test ROM that was newly written for this machine pretty recently, that wasn't working either. I basically am totally stuck with this computer not working at all, even though the whole computer is so simple and you'd think should be really easy to fix. So in this video, I want to try to get this thing working, and if I can, I want to give it some upgrades. So without further ado, let's get right to it. So it's been a few days since I've last worked on this machine. That's given me some time to contemplate and think about what's going wrong with this computer that's keeping it from running. As I mentioned in the intro, I swapped out the CPU, so that's not the problem, and I checked the ROMs, swapped those out, that's not the problem, and even tried a dead test ROM that should be able to diagnose issues with this computer or help diagnose issues. That doesn't even run at all either. What I have figured out is that the thing acts different depending on if you have the CPU installed or not, and the ROMs installed or not, and you put different ROMs in, you get different results depending on what configuration of things you have. So it feels like this thing is trying to run code and then it stops. Now, I mentioned in part 1 that one of the issues with this computer is that the construction quality is very cheap. And the cheapness isn't just the construction of the case and the plastic and things like that and these bodge wires. Even the PCB itself is pretty low quality and very easy to damage. When I removed the CPU, when I assumed that was the problem, I ended up lifting 2 of the pads on the back. These weren't pads that actually connect to traces. These are just single pads with a through hole via, and the trace is on the other side of the board. So lifting it on the back side isn't really that big of a deal as long as when I reinstalled the socket that the CPU sits in, there's a connection to that trace. I was pretty confident that when I reinstalled the socket, I flowed enough solder through the via that it should have connected the pad on the other side of the board to the pin. And that was backed up by the fact that when I had the original CPU in the socket, the machine was acting exactly the same when it came to not running any software. Theoretically, if those 2 pads were never connected, I would have expected slightly different behavior on the system when I powered it up with the original CPU and the original ROMs in place. But everything was identical with the sort of random stuff that we were seeing on the oscilloscope and on the screen. So I kind of assumed that those pads were good and they were connected. Now, in the intro, I mentioned the broken trace, and I talked about it in part 1, but here it is as a refresher. There was some kind of a scuff on the board, and it actually ended up breaking that trace. It didn't look any worse than these other traces. They look connected, and I did go and verify when I fixed this trace that these other ones were connected. Oh, really, Adrian? I really tested everything, huh? But sure enough, the signal that went from this connection, which is on the RAM chip, to that via, it was not good. There was a signal there coming from the CPU. I think it was address line 11 if I recall, but it wasn't making its way to there. And this is absolutely used by the ROMs. This via goes to a trace on the other side, which makes its way to address line 11 on the ROM chips. And I'm very confident in saying that that broken trace that was on this board would have kept this computer from working. But now that I've corrected that fault and we have address line 11, the machine's still not working. But in my thinking now about what might be wrong with this thing, now that I fixed this address line 11 and I know we have a good CPU and I know we have good ROMs in, perhaps there are other bad connections now. And it's quite possible that those connections were good, except for address line 11, which was broken and that wasn't my fault. But these new faults that exist on here could easily have been caused by me removing the CPU and removing the ROM chips. So I think the next thing I need to do right now is we need to go and validate that every address line and data line is making their way from the CPU to the actual ROM chips. And normally when you're going to do that type of checking, if you're looking for a bad trace or a bad connection, you just use the continuity mode on your multimeter. You try to beep out all of the lines. But I'm not going to do that. The reason why is when you have a connection that's very marginal, the issue is sometimes the beep mode can tell you it's connected and the resistance can be pretty low. But as soon as you put any kind of current through that connection, any kind of load, then you actually lose the connection. And that's something I've learned from working on cars throughout my life, that corrosion inside connectors can show when you use the beep mode that they're connected, but as soon as you try to actually put current through there, the resistance goes way up and the signal is not able to pass properly. So for testing the continuity on this board, what I'm going to do is I'm going to use this multimeter, but instead of using the beep mode, I'm going to use the milliamp mode, and I'm going to use a red LED in combination with the bench power supply to push a couple milliamps, or maybe 10 or 20 milliamps, through each one of the traces on the motherboard. And we can see the milliamp rating on there when we have this all connected. And if we're on address line 1, we're going to expect to see, say, 15 milliamps on the multimeter. And if we see anything except for that, like we see weird readings where the current is way less than we'd expect, then that is the trace or traces that I'm going to need to focus on. And I've gone ahead and I printed out the pinout for the CPU. Fortunately, this particular one doesn't have pin 1, so I'll put a dot there for pin 1. But this is the same arrangement as what's on the board there. That would be pin 1, so address line 11. And I'd already mapped out the pinout for the ROM socket with address line 12 there at pin 2. And that is in the same orientation as the socket, the notches at the top with pin 1 right there. And this red LED I'm going to be using, it's an old one, so it's pretty dim. I have the bench power supply set at 2.19 volts, but it's current limited to 15 milliamps. There it is lit up. It's drawing around 14 milliamps or so. Now the LED's power is going through this multimeter, and if we touch these together, there it is. That's the LED is turned on, and that is the current. So let's give that a test. So we're going to start on address line 11. I think that was the one that was broken. It might have been address line 12 that was broken. And there it is, address line 11. We're getting the full current through that trace. Now I'm going to say that is good. What I'm going to do is I'm going to go through all of the address lines, all the data lines. I think there's a read line as well. And if I find any that are bad, I'm going to put a little mark next to it, and then we will investigate further. All right, I've already found a couple small issues. I don't know if they're actual problems or not, but address line 9 and 7 are showing as low. So here's the example. This is address line 10, and notice we're at 16 milliamps, which is completely fine. But we go to address line 9, we're at 6.8 milliamps. And if we go to address line 7, which is that pin, we're at 8.9 milliamps. So I don't know if that's an actual problem, but that is definitely something we're going to need to look into. If I check that address line on both of these chips, it's low in exactly the same way. And I think on the SRAM is fine. 16.2 milliamps. And yet 9. So there's something going on, and it's obviously over in this area by the chips. Let's check the other one, address line 9, which was also low. I think that would be this pin. It's low on the SRAM as well. And you might think that like something is somehow sucking up that current. I don't think that's necessarily the case unless there's a short circuit. And that's because I'm not putting any kind of circuit on this. None of the chips are powered. I'm not going through any chip. I'm just going from a pin here through some traces to another pin. There shouldn't be anything to complete a circuit that would create any kind of load or anything like that. So unless there's like an inline resistor between those lines and these sockets, that's the only thing that could really explain this, or a bad connection. Okay, I just found another problem. We are looking at address line 7, so we know that's low. If I go to the next pin, which is address line 6, nothing. Nothing at all. How about on the SRAM? The SRAM is connected. Oh dear, but not the ROM chips. Oh man. Neither of them are connected. And that's got to be a problem under here when I reworked these sockets that caused this issue. So I'm going to draw an X there. And just to make sure I didn't somehow connect it to something else, I'm just going to check all of these pins. But that's okay. We just have to kind of go slow. Just watch the meter. No. Okay. And what I'm doing right now is I'm going through every pair of pins on the 2 ROM sockets. I'm just making sure that they pass current. The only pair that won't work are the chip select lines, because those go off to the IC that decodes that stuff. Everything else is in parallel between these. And so far, Everything is perfect. The other thing I can do is I can check, well, most of the pins are the same between the SRAM and the ROMs as well. So I can go ahead and do that same check there, which I'll just do right now. All right, when it comes to the connections between the SRAM and the two ROM chips, the only two that are problematic is the break for address line 6 is over here. It's not under the CPU, but pin 3 or address line 7 between the ROM sockets, and this is also low. I think it was like around 8 or so milliamps. And I think that coincides with what we saw on the CPU, where if we went from the CPU socket to pin 1 on the ROM, we got full current draw. But then when we went over here, we only got 8. Yep, so that problem with the high resistance is over here as well. But what I saw is address line 9 from the ROM socket to here was fine, no issues, but it's low coming from the CPU, which means if we go from the CPU socket to the SRAM, there we go, 6.4. So the problem for this one, this exists, well, somewhere in between these 3 chips and the CPU socket. So that could be my bad connection under the socket with that pad that came off. All right, here are the results of the testing. I tried to clarify it a little bit. On the CPU, everything with a tick mark is actually good on the CPU socket. So even though I have address line 6 with an X, you can ignore that, and this L you can ignore. Those problems exist on the area of the motherboard that connect the RAM or SRAM chip over to the ROM sockets. I think those are just parallel traces, and that's where this problem exists, this low resistance and the X. Address line 9, on the other hand, the high resistance we're getting is actually happening between the CPU and the SRAM and the ROM sockets. So I think that problem probably exists over here, or, well, we don't know where it exists exactly, but it's somewhere else. Now, the other signals I haven't validated are any other outputs of the CPU that are used for address decoding. So these 3 address lines are a perfect example. And I don't think, oh, maybe the write signal, that's necessary for the SRAM to be able to write to the SRAM. Let me just quickly check that. The write signal is pin 21 that goes to the SRAM. That's no problem. So I think from a problem and troubleshooting perspective, first thing I need to do is figure out what's wrong with address line 6. There's no way the system is going to work with address line 6 disconnected to the ROMs. Clearly, that's probably what's keeping the system from booting, and that certainly came from when I reworked the motherboard over with the ROM sockets that caused that fault. Let's take a look at address line 6 between the SRAM and the ROM sockets. Well, yeah, meg ohm. So that's no good. If we go up to the pin above it, oh, that's one of the high resistance ones. 15 ohms? Well, that's not right. That is not right. If we go down to address line 5, that should be this. There we go. 0.1, 0.0 ohms, whatever. That is what it should be. 15 ohms on the other hand? All right, so looking at what's happening here, this is address line 7, and that has low resistance to the ROM sockets. See right there? Something's going on in that spot. And that pin is just paralleled with that one. And the one that's disconnected entirely is this pin, address line 6. And notice it's got the whole scuff thing going on. Is it broken there or is it broken here? Probably broken. Okay, so that's the one that's low resistance. It still beeps the multimeter. This one, on the other hand, doesn't beep at all. Where is the break, though? Is the break right around here? No. Let's see. So I can poke it there. How about here? Nope. The break is there. It's in that spot again. And I thought I went ahead and I checked this stuff, but I obviously didn't. It's time just to use this Dremel tool to just clear off all of this. I'm just gonna see what's going on underneath there. All right, well, things look bad. I mean, they look bad all around here. Let's just see which of these aren't actually connected anymore. Now that I've removed this, it's very easy for us to check. So even though it doesn't look like it's connected, I think there was just a dent in the board. It actually is connected. Yeah, that one's fine. Let's see about this one here. That one is connected, even though it doesn't quite look like it is. That one is fine. This one, yep. It's funny how it looks broken, doesn't it? Let's check down here. Okay, that one's good, even though it doesn't look super good. That's broken. That one is connected. That one is connected, and this one looks fine. Yep, that one's fine. All right, I think what I need to do, we're gonna put a bunch of flux here, and I'm going to I'm just going to tin all of this stuff, try to reinforce it. Now that I've tinned those, you can see the gouge, and unfortunately, we still have bad problems there. So I'm going to have to get some very thin wire and reinforce those over the top. All right, that's an ugly repair. I haven't cleaned the flux off yet. Let me double check what's broken, and I think we should be good with all those connections and the low resistance. Okay, address line 9, that pin appeared to be low resistance going to these sockets, but I think again it was the break that was causing it. So we're looking for address line 9, that's this one. Yep, less than an ohm. And then we're going to go to address line 7. There we go, less than an ohm, that's good, that was low. All right, address line 6, which goes to the SRAM right there. Okay, I still got to fix that. It's still broken. Between the static RAM chip and the ROM socket. Oh, one more fix to make. Obviously, the break appears, I put a bodge there, but I must not have connected it properly. You know, one of the things that happens here is they're so close together, it's easy to dislodge one while you're working on another, or create a short. Okay, that is not it. It's this one. It's still disconnected. I think I was actually just doing the wrong one. And I just dislodged it and got it connected to the one above it. You gotta be kidding me. Oh, come on. This type of work requires a very steady hand. It feels like I am not doing such a great job here. Okay, I think that's it. I think it's finally connected. Really, we have to check from the top side. So address line 6 was broken going to pin 4 here. There it is, less than an ohm. So I'm just making sure that it's not connected to any of these other pins. Same, I'm just gonna quickly check the other ones as well. So I'll just stay on the one pin on the CPU. Just check both rows of pins on the socket. So we're looking at address line 8, which should be on this side. There it is. Not on any other pin. Address line 9. There it is. Not on any other pin. That's good. And then address line 10. It's down there. Resistance looks good. And I gotta check address line 11. It should be over here. There it is. Just make sure it's not on any other pin. Looks good. Now we're on address line 12, which should be up there at the top. Let's make sure it's also not shorted to anything else. Okay. Yes, I think it's all done. All right, well, I think what I need to do now is clean this up, just get the flux off here, and let's put the dead test ROM in here, and let's see if this thing works. Okay, here we go. 3, 2, 1. I heard a beep out of it. Oh. Well, okay. It did something. It definitely beeped out of the speaker. Let me power cycle it again. Yeah, without a doubt, it's beeping out of the speaker. But we're not getting any display. No, so there's still issues. There are still issues. You know what? I hate this piezoelectric beeper speaker thing. I'm gonna hook a real speaker up to this thing. You know what? It just connects to that pin and that pin. Maybe I shouldn't hook a regular speaker up to it. I think I'm gonna find a little piezo beeper thing like this, just from like a PC speaker. And let's check the resistance on this little piezo thing. I mean, is it bad? What about this one? That's 12 ohms. And of course the speaker, it says it's 8 ohms. I'm not sure that hooking a speaker right up to that is necessarily the right idea. What is that chip? It is an HD 74LS174. I checked the datasheet for the 174, and 16 milliamps is the maximum current it can sync on any of those outputs. And with this, I think it was 12 ohms. That's way, way too much. But If I put a 1K resistor in line, I don't know what that'll do to the volume, but if I put a 1K resistor in line with, say, the speaker, then maybe it would be too quiet to hear anything. I don't know, but it would also bring the current draw down to just 5 milliamps, which I think should be within the safety region of this IC. I installed a pin header, and on the bottom side, I cut one of the traces, put a 1K resistor, and have this 8 ohm speaker hooked up. And when I turn it on now, there's a beep, but it's really quiet still. So I guess if I want to fix this, I need to figure out a little amplification circuit or just live with this incredibly quiet sound that this thing makes. All right, the bench camera has run out of power again, so I won't be able to show the board while I'm working on it. But as we can see, we get a beep when we turn on the dead test, and we get that pattern, but that is it. No matter what I do, I can reset the thing multiple times. It just always gives us that exact output. I think what I should do is install these EPROMs that have the regular basic operating system on this thing. Again, with these dead test ROM, I've never seen it work before, so I don't really know what happens on a real machine, especially a 2K machine like this. So let's try the actual OS and see what happens. Okay, I think I have the basic ROM installed correctly. Let's see what happens. Oh, it freaking works! It freaking works. Very interesting that the dead test ROM does not work. So yeah, there is that. Video technology, basic version 2.0 ready. I can't believe this is actually freaking working. Now what's interesting here is that this sort of proves that probably the problems we've been having the entire time was that scuff mark with those broken traces. And in that repair work I just did earlier in this video, part 2, I only was bridging over where that scuff mark was. I was not fixing or touching up any of the solder joints on the CPU socket or the ROMs. So this damage was on this board when I got this machine. This wasn't something that I caused by my rework. And what sucks is we know that these 2 ROM chips are actually good, and the entire problem this machine has had since the very beginning were those bad traces from that scuff mark. And it's funny because we have to think about, where did those come from? The machine looks mint. Was this a bad machine from the very get-go? Was that scuff there from manufacturing? And the reason why the thing looks like it's unused is because it never worked properly? Since Tommy from Arctic Retro sent me this machine, and I don't recall in Tommy's letter if there was any kind of background information on this machine. I don't think there was. I think this was a machine that Tommy tested briefly and it just didn't work. So he sent it to me to see if I could get it working. And well, finally, years later, I did. I actually did. All right, well, what we need to do now is we need to see if this keyboard is working. So if I pop the case apart, I have the little connector I soldered onto the crappy ribbon cable. And I have the keyboard now connected onto that pin header that I installed, and the power LED is on. And does this actually work? This works. Oh, wow, it does work. Wow, typing is terrible. Okay, so I hit the exclamation point, sometimes it types multiple. So we're talking little rubber contacts under there like a remote control, and those definitely kind of crap out with time. I've dealt with trying to fix these in the past, and it's pretty difficult. I bet you there's a PCB with the little gold sort of interleaved contacts, and then the rubber keypad, like a remote control, has a little carbon impregnated pad and pushes down onto there. Sometimes taking apart cleaning it can help, but other times you have to use a special conductive paint on the rubber pads to try to rejuvenate it. Let's see if this thing is actually working. It is. Yeah, I think maybe just with a little bit of typing, it's fine. It feels freaking horrible. I mean, are we surprised it feels horrible? No, right? You really have to push right in the middle of the keys. Oh, it's bad. The ZX Spectrum keyboard actually is way better than this. This feels miserable, and I don't think it's because of age. I think it was like this from the very get-go. Now, as for the shimmering you see, I think that has to do with this terrible chroma decoding board. I think it's not locked to the clock frequency of the computer. Therefore, there's a lot of drift. And yeah, if I kind of touch it, I can see the shimmering is changing as I touch it. I'm typing in a little program here. I can tell you, the keyboard is absolutely miserable. It is so miserable to type on. Probably a slight step up from the Timex Sinclair 1000, aka ZX81, but barely. It's really bad. I can see why the 300 with the real keyboard had some success according to the Wikipedia article, because at least that you could type on it normally. All right, I'm back, and it's been several hours. I just left the computer turned on and running. I wrote a little basic program before I went upstairs, and all it does is it prints every possible character to video memory, which happens to be the normal letters, inverted normal letters, and then these semi-graphic characters, which are also printed in the 8 colors. In addition, every time it loops, it switches the background color from the green to the orange, which you see it doing there. And it's also inverting the text, which is why sometimes the first 2 lines are inverted, and then the other times they're not inverted. So if we hit Control Break to get out of there and we list the program, you can just see what it is. It's very simple. Now on line 60, this poke 26624 is the latch, and bit 16 is what changes the background color. And then this one here is what inverts the screen, 30744, Q, so either 0 or 1, and that inverts it. Currently, you can see it's inverted because the background is sort of a dark green while the text is a light green. And to reiterate, the graphics chip that's in this and the color computer and the Dragon, it does not support white text on black background. It just can't do it. You have 2 possibilities. You either have a green background, either dark or light, or an orange background, either dark or light. Personally, I feel it's kind of a strange color scheme, and I don't really get what went through Motorola engineers' minds when they came up with this particular design. But one thing we can tell is that this computer does appear to be working without any issue. So what was going on with the dead test ROM? Well, because of course it's open source, let's take a look at the source code just to see what the dead test ROM is trying to do. All right, here's the GitHub repo, and the code is written by Reese Witherly in 2024. And my Z80 assembly language skills aren't that great, but there's a lot of commenting on this code, and I think we can pretty much figure things out. So screen memory location, 7000 hex, that is correct. And here's where the start of the main loop is. So set the stack pointer to 7800. That's an untested memory. And one cool thing about the Z80 is you can set the stack pointer anywhere, unlike on the 6502 where it's fixed. That means that if you have working video memory, like this machine, well, should have, then the stack pointer can actually exist in the video memory, and you don't need the regular RAM on the motherboard for doing anything that requires use of the stack. So it looks like what's going on is it's copying the test screen. So it must be a data set, maybe at the end of the source code, to the video memory. So copy test screen, topic test screen. And if we zoom to the end, let's see if we have the test data here. So my assumption is when we turned it on with the test ROM in there and there was all that stuff that looked like garbage on screen, it probably was this, 256 bytes from AES SBox. It's probably a good set of data for doing a RAM test. So after copying the screen, it does a beep loop. Okay, so we heard the beep out of the speaker, so we know that was working. So this is all part of the beeping. And now it's comparing the test screen. So I think what it does is it writes all the test data into the screen memory, and then it reads it all back, and it compares the read back results with what's in that array down at the bottom. And if anything goes wrong, you get video RAM failed. And if it's working, it prints OK on the screen. And if it's not working, RAM failed, it prints bad, and then it jumps to probably infinite loop. Then if it's good, it goes on to check for like VSync stuff, probably to tell if it's 50 or 60 hertz. And then it goes on and does more stuff. Okay, print some stuff to screen. And we saw the test screen for the dead test ROM on the GitHub repo. It prints a bunch of stuff on the screen. That's obviously what's going on here. So let's go back to the dead test ROM. And let's just see what it's doing exactly. I don't have the speaker hooked up at the moment, so we won't hear the quiet beep. All right, dead test ROM is in. Notch is in the correct position. Turn this on. Okay, it looks like on the 4th row down, over on the far right side, there's bad printed there. That's gotta be from the test routine doing the whole comparison, and it wasn't able to read and write from the video memory. Why is it printed over there, way on the far side on the row 3, and not just like at the top left corner of the screen? I don't know. But yeah, that was funny. I didn't see that the first time around because I didn't know I was supposed to even look for that. And it's just sort of mixed in with all other garbage, so it's not easy to see. But what this really tells us, I think, is that this is failing on the test routine that's reading back the VRAM. In my humble opinion, if you're writing a ROM to do something like test the VRAM, which you're then going to use as a stack pointer area, so you can't run the rest of your diagnostics without the working VRAM, you should try to do as much as possible to let the user know that the VRAM is bad. Therefore, on this machine, imagine if you had no VRAM chip at all, like it wasn't there. You wouldn't even be able to see that bad message. So what you should probably do is, if the speaker is working, which we know it is, when you go into the infinite loop, when you have bad memory, you should just beep the speaker forever, like beep, 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 beep. The other thing you can do is the 6847 video chip has the ability to switch the color palette, or the background color that is, for the text. And if you had a bunch of garbage displayed on screen because your video RAM chip is bad, toggling that background color bit, which is not done through the VRAM, that is done through the latch. And if you did that every, say, second, green, orange, or some certain amount of time, or you beep the speaker for a second, then you flash the text orange for a second, and then you kind of alternate, that's a great indicator for someone that, hey, your VRAM's not working, because if you look at the README, it says, you know, if you see this and hear this on the speaker, bad VRAM. And you don't even need to have a working VRAM chip to see that working. Anyhow, back to the problem we're having here. So the ROM says we have bad video memory, but clearly the video memory at least works to some extent. I think what I need to do is, let's go back to the standard basic ROM, and what I can do is poke and peek the video memory. So I can actually write a little basic program that just writes some values into video memory and then reads it back. And then we can see if basic is able to read and write from the video memory. We know it can write to memory because it prints stuff on screen, but maybe it never reads back from video memory, and therefore maybe that part of the circuit is bad. Okay, first thing I want to do is I want to invert the screen. I find the green just really off-putting. So this should invert it. Yep. So using the Windows calculator, I converted 7,000 hex to decimal, and that's 28672. That's the start of video memory. So if I poke a value into that address, like I'm going to put a 0, and I'm assuming the V in the top left corner should become an @ symbol. And there it is, that worked. And then if we do a peek to that same memory location, we should get back a 0. And we did. So let's change this value to something else. I'll make it 234, which is a purple line. And now if we do the peek, 234. So that means that, at least for that one memory location, the computer is able to read and write from the video memory. So what I need to do now is just write a quick basic program that just uses a for loop to just iterate through all the memory locations, which is 28672 to 30719. That is the full 2K of memory. Fill it all up and then read it all back. And if anything reads back with a value that isn't expected, stop and clear the screen and then say, you know, this memory location has a problem. All right, here's the basic program I came up with. So it's just a simple for loop, 0 to 2047. That is 1 byte for every 2K in the video memory. And then it sets P to 0. That's the value we're going to poke into memory. So I'm going to do 0, and that's what 28672. That's the first address of the video memory, and then plus I, that's the offset. And then it's poking 0 into that, and then it's just immediately peeking it back and stores it in a variable called VRAM, and if the VRAM is not equal to P, then it just prints error and exits. Then it sets P to 255, so that's all ones. It does the same poke, it does the same peek, it does the same comparison, and then if there's an error, it also exits, then it just does a next, and then it prints done once we're finished. I haven't tested this yet. Let's see what happens. This should clear the screen. We should see it go through and do the whole screen. Okay, there we go. So what it's doing is the @ symbol you see briefly, that is the value 0, and then this orange box, I guess, is what all Fs looks like in video memory. And there seems to be a little bit of static as the system reads and writes from the video memory. That's obviously some contention with the refreshing of the memory. Hey, that's weird. Are we having an addressing error? I think we might have an addressing error to the video memory, because it doesn't look like it's actually writing to the upper parts of video memory. It was like it was looping. So 2K of video memory, one whole page of text on the main text screen takes up first 512 bytes. Then theoretically you have 3 additional pages of 512 bytes that shouldn't be visible to us on the monitor. But it went through and did the whole screen, and then it did it again. This very simplistic RAM test here is not going to catch any kind of page errors like that. And a page error would be if we wrote to a memory location outside of the text area, but due to an addressing error to the video RAM chip, it actually wrote part of text memory we can see. And maybe what's happening is the second to the top memory address line is stuck, or it's not getting through. And therefore, even though we have 2K of memory, the first page is mirrored, and then the second page is mirrored as well. Okay, so one way we can test that is we can start this. I need to do insert. This is very much like the Commodore editor, by the way. So Microsoft made this basic, and it works in a very similar way. It's not as good as the Commodore one, but it's nearly as good. I didn't mean to actually do what I just did. What I want to do is insert right here. So if we start at 512, then theoretically we should not be writing to the visible part of the screen at all. It should only be testing the upper part of memory above the visible area. Now we just go down to the bottom and we do run. And no, yeah, it's writing to the actual memory that we can see. So you saw it did one page, and now we're not seeing it. Well, I'm assuming what's happening is it's writing to that upper part of memory, and it's doing it twice. It's just my simplistic test here is not going to catch any kind of problem. And this is actually something on the Apple II Dead Test ROM that David Giller programmed into it. Is I asked him to add this type of page error detection right into the routine, and it is able to do that pretty well. And we saw that the Dead Test RAM test is better than what I'm doing here, but still very rudimentary. It's good enough to detect there is some kind of a page error because it's copying that AES block into the RAM and must be doing it multiple times. And because it must cross the page boundary, what happens is it copies it and it copies it again, and part of that second copy overwrites part of the first copy. And when it goes back to verify, well, that first copy has now been overwritten. Therefore, that's detecting the problem. All right, I'm going to modify this program to try to detect this page error. So I did a very small change. I'm looping now from 0 to 1023 only. And what I'm doing is I first write to the VRAM memory location with value P, which will be 0 on the first part of the loop at the top there. But right after I do that, I'm going to poke video memory again, but offset 512 bytes with a value of P plus 1. And if this page error is happening, what will happen is when it goes back to read that first memory location, instead of getting back a 0, it's going to get back a 1. And then it should print error and then end. So I predict as soon as I hit run, it's just going to immediately error out. And yes, it basically did nothing because it errored immediately. So this particular problem is a page error. This is not a chip select problem. The RAM chip is being selected properly and being written to. It's that the address lines coming from the CPU aren't making their way to the RAM chip properly. So this is the problem this chip is having. When we write to memory location 0 or 512, it writes to the same place in the chip. We don't know where it's writing. It could be writing to the beginning at 0, or it might be writing to 512. It just depends on what's happening with this address line. See how there's a 1 there? That's the address line we actually have to look at, and that's the one that's going to be stuck. It's either stuck 0 or stuck 1. So starting from 0 over on the right side, address line 0, we're going to be talking about 8, 9, address line 9 going to the VRAM chip. And our video RAM chip has 10 address lines, which is what it needs for 2K, but we need to look at pin 22 on that chip, and I predict that that signal probably is going to be stuck. Now there's actually something else we should do, is we should set the video chip into graphics mode where it will use all 2K and display it all on screen all at once. Because we don't really know where this broken connection is. We don't know if it's, say, right at the socket, so all of the signals, either from the graphics chip or the CPU, are broken, or maybe it's this whole resistor array that connects the address lines from the video subsystem to the CPU. Maybe the problem is there. So it's possible that 6847 can address line 10 properly, and we'd be able to see it on the oscilloscope. We'd see activity on there in graphics mode, but anytime we try to write to the video memory from the CPU, if it's broken over here, well, that's going to be a problem. So let's turn on graphics mode and run this same test again. And let's alter the loop so it fills up all of the memory. Well, let's just rem out these statements. Now let's see what happens. Okay, well, we can see the page error in effect right now. I'm only writing to one memory location at a time, not two. So what's it doing there? That's something wrong, obviously. There it goes in the bottom half. And it's mirrored. It's also page errored. This actually tells us something. Now we can't tell what's going on because it's just a whole bunch of garbage. But before it wrote all this mirrored information into the video memory, what we could see is that we saw like bands of clear and bands of stripes and stuff like that, which tells us that the video chip itself can see all of the video memory. I'm pretty sure that we're going to find that if we look at the address line pin on the memory chip, we're going to see plenty of activity there, but that's coming from the video RAM chip refreshing the screen. As it redraws the screen 50 times a second, because it's a PAL machine, it has to access all the memory locations of the video memory and read from it. And it's only when the CPU is trying to read or write to the memory that the address line is getting stuck. All right, so we determined that DA9, if we check that, it'll actually have continuity through to pin 18 on the video chip. But DA9, over here on whatever resistor this is, A9's on the other side of it, I think the problem's gonna be there, or it could be over on this side of the resistors. It's definitely something to do with DA9 going through to the CPU. So let's investigate. Okay, first we're gonna check continuity between pin 18 on the 6847 and pin 22 on the SRAM. All right, there it is. We're at 0.18 ohms. I know you can't see that, but that's a good connection. Now I want to see which of these resistors is connected to address line 22, or sorry, address line 9, which is on pin 22. That's pin 22. There we go, it's that resistor right there. So this resistor, 6.8K, that's exactly what it says in the schematics. And now we're looking for address line 9 on the CPU. So if we go from the pin on the CPU to the pin on the chip, address line 9, we get nothing. If we go to the next one, which is address line 8, 6.8K, which is exactly what we would expect. But we have address line 9 going to the resistor. On the bottom of the resistor, we have 6.8K, so the resistor is not open. It's open from the bottom of the resistor to the pin on the CPU. It is open. So on the bottom, there must be a problem with something. Incidentally, I had to repair the wiring on this little board. You know, so there's a yellow wire now, and I put some hot glue because just moving this around, the wires were falling off, and I lost the color, and yeah, annoying. Okay, on the bottom of the board, address line 9, the trace is right there. There's nothing. There's nothing. This is the resistor. The trace does not look broken. Use the pointy tip to try to poke through. Okay, so it's there. It's literally broken. It must be broken right at the pad. Oh, this board is junk. Ignore this blue bodge wire. That's for something I'll talk about in a moment. It has nothing to do with what's going on. This is the pin in question. There's the trace. It goes to the resistor right here. There must be a trace on the other side of the board that connects it to the ROMs and the RAMs, because that trace only goes there. But the break, it literally must be like right here. I'm just going to scratch away the solder resist with from the pin itself to the trace. Yeah, it's broken. So that must have happened during the rework. It just shows how unbelievably fragile this thing is. And now it is connected. I put the tiniest of bodges on there, just the tiniest of wires. And now for the test on the top side, 6.8K, and it should go to pin 22. It does. That was it. So if we pop out the ROM and we put back in the dead test, oh, there it is. It's working. So that was it. 2K of RAM. V6 signal, video RAM, okay. It freaking works. Page error problem. Now here's the thing. As I mentioned, the Apple II ROM can already detect this kind of stuff. I'm definitely going to pass that information over to Reese, who made this ROM, to hopefully add that functionality into this, because page errors are a real thing and they're hard to figure out, because just having bad for your RAM doesn't really give you any information of, well, what exactly is going wrong. And with a very quick and simple test routine, you can detect page errors immediately. And you do that before you even test the main RAM, because there's no point to do the full RAM test if there's a page error, because you're immediately just going to fail out anyways. So hopefully that can get implemented in this ROM, which will make it a lot more useful. Now, as for the shimmering, by the way, there's a variable capacitor on this little board. It has all sorts of effects on the image. In fact, I turn it a lot. It can like go black and white like that. Like we've lost the color carrier altogether. I don't know exactly what this is changing, but if I get it just right, it kind of stops shimmering like it does there. Problem is, just putting my hand near it or it heats up, it starts to shimmer again. So I think it's just a really badly designed circuit. I think that's what's going on. Okay, well, I'm confident in saying that this machine now is fully functional, which is awesome. The one thing about it is it's only got 2K of RAM, which kind of sucks. I think we can add extra memory to this thing. And I'm kind of glad to have gotten the dead test ROM working, because since it detects the amount of memory that is available on here, I think with something like this, a 32K SRAM chip, which has nearly the same pinout of these 2764s, except for has a couple extra address lines and a write line, and plus a different chip select line, I think it might be possible to piggyback the RAM chip on top of the ROM chip, run the extra lines to the RAM chip using some bodge wires, and create a chip select line for it. And this thing will have 32K plus 2K, so 34K total, which is the maximum size allowable without bank switching. And we can do that without a whole bunch of mods, and it will all be internal to the system. And I think that's worth it, because 2K, it just kind of sucks. There are games for this thing, but I doubt they're gonna work with 2K of memory. Now, if we go back to this worksheet I created for the comparison between the original ROMs and the 2764s, if we flip this over, here's the pinout for the 62256. That's the SRAM chip that we're talking about here. When we look at the pinout between these two, it's nearly identical. We have two extra address lines, A14 and A13. That's in the non-connected and VPP pins. There's the write enable pin, 27, and that's just 5 volts on that socket. And then we just have the chip select line. So if we take this and we put it directly into this socket, it's not going to work. I mean, it will work. We'll be able to read 8K from the SRAM chip in the same address space of this ROM, but since we can't write to it, it's just going to have some garbage in there when we power the system up. What I need to do is I need to create a new chip select line for this chip that turns this chip on anytime address line 15 is turned on. Remember, the Z80 has 64K of memory space, and address line 15, which is the highest address line, delineates the top half or the bottom half of the address space. So 32K and 32K. Currently, everything that happens on this system happens in the lower 32K. So address line 15 is always high. Well, we can't just use address line 15 as a chip select line because A, chip select on this needs to be low, so we need to invert that signal, but it also needs to be ORed with another signal that comes out of the CPU called memory request. And that's asserted anytime the Z80 is trying to access memory. And this is as opposed to I/O requests. So if you know your IBM PC architecture, you know the whole I/O addresses and stuff like that, well, the Z80 has the same thing. So there's a separate line that's just not used on the system at all that says if the I/O addresses are being written, there's different instructions in assembly, then assert that line, otherwise you assert the memory request line. Now the thing is, on this particular system, the I/O addresses aren't used at all. So nothing should ever be trying to read and write from the I/O addresses. Also, I'm pretty sure the I/O address space on the Z80 is only in the lower chunk of memory, so it uses the same address lines, but it doesn't ever use the address line A15. That line will always just be 0. So theoretically, we could create a chip select line for this RAM chip, the upper half of memory, by just taking address line 15 and inverting it, and then feeding that into the chip select line on this chip. Theoretically, that should do the trick. Now, this computer is pretty simplistic. There aren't a whole lot of logic gates, but a lot of times when designers are designing a system, they're putting TTL logic, they often leave gates unused. Well, I went through and looked at all the gates that are in use on this board, and I figured out that the one gate that we need, the inverter gate, there was one that was left free. That's what these blue wires are. So this is connected to address line 15, which normally I think just runs off to like these expansion connectors. Ignore the hot glue little lines there. So what I did is on this IC, that first inverting gate is just not used. It's not hooked up to anything. So I fed address line 15 into it. And oddly enough, you should never leave TTL chips with their inputs floating. But the designers of this board, which notice there aren't even bypass caps on here. They did leave it floating. So I just connected it to address line 15, and then the output, I just ran it through this bodge wire, through this hole in the board, and it pops up right here. Now, unfortunately, I should have made this longer. I don't know what I was thinking, because I think it would be best to put the chip in this socket. I mean, ultimately, we need that in there, and then this would have to be soldered on top of it, but with the chip select pin bent out, plus the additional address lines bent out. But for testing purposes, let's bend out the chip select line, so pin 20. And without even wiring up the additional address lines, this should give us 8K of additional memory. Now, I just noticed, I was trying to straighten the pins, and I noticed that that one isn't so great. It just broke off and fell on the motherboard. Okay, there it is. I didn't want that shorting something out. And I will need to attach an extra pin onto that. So we'll just steal it off this dead Apple chip. This must have been from an SE30 from the machine that I damaged. So at least one of its pins will go to save another chip. This is really just a proof of concept. If this works, then what I'm going to do is I will bend out these extra pins on this and run the extra address lines. And that should give us the full amount of memory that we are looking for. Hooking up the RAM this way will create a page error. And that's because this is a 32K ROM and the chip select is also for 32K. But because we're missing the two address lines, it's going to have 8K just repeated 4 times. And maybe the dead test ROM is not going to have a problem with the page error, but you know, it probably will, because we already saw that it did for the video memory. All right, here we go. Okay, still only detecting 2K of RAM. Oh, of course it's only detecting 2K of memory. I didn't hook up the right line. It's not just the address lines, it's the right lines as well. All right, I'm gonna go and hook up the address lines and the right lines. I just need to bend those 3 extra pins out, and then this should work. Alrighty, all the bodges are done. Obviously, I haven't soldered this on top of the ROM chip. We will do that once we know that this actually works. We have address line 14, address line 13, we have the right enable pin, and we have the chip select signal, which is the inverted address line 15 that comes from this unused gate on the 74LS04. And on the bottom side, I tried to use a little bit of hot glue to keep the bodge wires looking good. I realize now the right enable pin, which I picked up off the CPU there, I could have actually got it from these extra pins for the RAM expansion board. And actually right enable is also on the RAM chip here, so I didn't need to do that. I could have done it down here. But whatever, 6 of one, half a dozen of another. And at this point, when I turn this on, I expect the dead test ROM to see 34K of RAM. So let's see what happens. Or it's not going to work at all. Maybe I ruined the computer. 2K of RAM! 2K of RAM! So I think what we need to do is check some signals. All right, so this is the right enable pin. So it's making its way to the RAM chip. That's what I wanted to check. Oh, you know what? That's wired up incorrectly. That's the right enable pin. And I have that connected to something else, obviously. Well, I might have swapped it with the address line. I don't know. Yes, I think I did exactly that. This is address line 13, or supposed to be address line 13. Meanwhile, if I go on the CPU and we look at address line 13, yeah, okay, so I swapped those 2 lines on the RAM chip. Easy peasy. That's an easy enough fix. Why don't we just check address line 14 while we're at it. Let's see if that matches what the CPU address line 14 looks like. It does. And then this signal here is the chip select, the one that's coming from that inversion gate. I'm curious, if we power cycle the computer, we should see that actually trigger. In fact, I'll put this on normal mode, so we'll only see it when it triggers. Okay, there was at least one. Oh yeah, okay, a whole bunch of writes. So that would be the ROM trying to write to the memory, but obviously it's not going to be able to because I have the write line swapped with the address line. Let me just quickly fix that. All right, those lines have been swapped. What's going to happen? Oh, it's unhappy. It is. Oh, wait, what? RAM size at? So, I don't know. Is that a bug? I mean, it's saying RAM data lines are all okay. It took a while. Let's do that again. I think it's detecting all the memory. It's gotta be. Let's recycle the power. Yeah, this thing must not support 34K of RAM properly. I thought I saw in the code that it did support 34K. We'll have to take a look, but I don't know. It's not, it's better than being broken, which is a whole lot of what I've been seeing with this thing. Report the size of the RAM that tested good. It loads a table called RAM sizes. Let's find that. Okay, here are the RAM sizes, and 34 is seemingly supported, but it was printing at, which kind of implies that it went out of bounds on this little database of strings. Yeah, there's the problem. The database is going in 1K increments, but it goes 32, 34. There's no 33. There needs to be a 33. So it's printing the value after 34, which is just two nulls, 0, 0, 0, 0, and the ASCII value of that is at. So I'm totally confident this RAM expansion was a success. And what I need to do now is just lift that chip out of the board, piggyback it on top of this EPROM, solder all the legs together, put it in the socket, and then we should be able to boot into BASIC. And I know the command in BASIC, or the way in BASIC you can figure out how much RAM you have, because it also counts up the free RAM, and it should be reporting, you know, 30K or something like that, 31K. So let me go do that butchering of this chip, and hopefully we'll have a 34 kilobyte VZ200. There it is, it's done. It's piggybacked on top. And I mean, it looks weird, but you know what? 32K RAM expansion in a VZ200. Has anyone ever done this before? There's probably folks watching who had one of these computers and maybe read the magazines or newsletters or whatever that existed, and maybe this was a mod that people told you to do. I'm still gonna leave the dead test in there. This should just boot into the dead test again, and then we'll switch over to this basic ROM, the left one. All right, here we go, 3, 2, 1. This black screen, it's always a bit concerning, but yeah, I think it's gonna work. Oh, there it is, at RAM. Okay, keyboard is reconnected. The basic ROM has been reinstalled. Okay, here we go, 3, 2, 1. Power lights on. All right, lots of shimmer, but it is working. Okay, to see the free memory, it's kind of weird and obscure. There is no banner that prints like on the Commodore BASIC, which incidentally is interesting because there are 16K of ROM between BASIC and the OS or whatever that's on here, which is exactly the same as on the Commodore 64. And yet Commodore was at least nice enough to give you a welcome bar that showed you how much free memory you had, which is obviously left over from the Commodore PET, which had various RAM configurations. Right, so to do this, you gotta do print, parentheses 0. Now this is kind of strange, and I had to look this up on how to do it, and I found this in a newsletter. It wasn't even in the original manual. And then what we do is we poke this value 31470,218. And what happens when we look at the list now, there'll just be a single print command. But when we run this, that poke changed that second token, which is print parentheses 0, to FRE parentheses 0, which on a lot of Microsoft Basics tells you the amount of free memory available to BASIC. For whatever reason, that command, free parentheses 0, doesn't work on this BASIC. But apparently the token is there. It's just hidden. If we run this, this should tell us the top of memory. Now, I wish I had run this before I added the RAM. I guess I could take the chip select line off. It used to show like 1,221 bytes free, something like that. And then I typed in a few more lines to this program, and then I ran the program again, and then it prints a smaller amount. So I expect this to be like 30,000 or 33,000 bytes or so. Let's see. Yeah, 33,994. Freaking works. So this thing really is a 34K Laser 200 now. How cool is that? So if we just add an extra line, hello, this is an expanded laser. There's a bunch of bytes there for the string, and we run this, it will tell us the free RAM, which will be less now. It's less than 33994, 33951. So we lost those bytes to that print statement. And theoretically, if we just erase that line, run this again, it should be back to 33994. And it is. It freaking is. I wouldn't be surprised if this Microsoft Basic, just like Commodore Basic, does a quick RAM check when you first power it on, and then that is used by the basic interpreter itself to know where to store the variables and line numbers and things like that. It's just silly that there's no command for free memory like there is on other versions of Microsoft Basic. All right, things are looking up on this Laser 200. Obviously, I have no way to load software like off an SD card or off a computer onto this, but I think I saw some utilities to generate WAV files to allow you to load it over the cassette interface using an audio file. So I'm going to do a little investigation to try to figure out how that works, and then hopefully I can load some games and we could try some stuff on here beyond the simple little basic programs that I've been doing so far. There it is. That's the Laser 200 fully reassembled. I did put a speaker inside. Since I left the RF shield out, I actually put a full-size PC speaker right under this vent. Actually, you can hear it now. So let's use a regular 9-volt power supply. It's just center positive. I have an audio adapter so we can load software on it. And this is the composite video connection. For loading software onto this, I'll be using this old prepaid Android phone, which still has a headphone jack, which is very helpful for this exact use case. With the machine fully assembled, I don't think I ever noticed this. When you turn on the computer and you type, you actually get a bit of a key click out of the speaker. Loading software is very straightforward. It's just C load, hit enter, push play on the phone, and I have it hooked up to the speaker, so I'm going to turn that down. And it says 734.bar or dash bar, and now we wait. When I was looking for software to run on this, there was a bunch of stuff, games, utilities, word processors, things like that. Oh look, this just loaded. The Graceful Blue Danube, high resolution graphics. Hit enter. As you can see, these are just some animated lines moving around the picture. Now I've run a bunch of software on this machine now just for testing purposes, and everything that has animation has this static that you're seeing. And I'm pretty sure this is coming from contention with the graphics processor and the video RAM and the CPU trying to access the RAM at the same time. As the video display processor refreshes the screen, it's doing that 50 times a second, it needs to access the SRAM directly. And if the CPU is trying to access the SRAM, well, it's going to create these types of artifacts as the CPU is accessing the memory. The 6847 has a 50 Hertz signal that comes out of it that goes to the CPU interrupt pin, and it's my presumption that software is supposed to wait for the interrupt before it updates the video RAM and do that within the vertical blanking interval. That way you're avoiding any kind of static. Either software is not designed to work that way, or the Z80 in this thing is too slow to copy all the RAM in time. So I don't know. But I did check to make sure that signal is making its way to the CPU, and it absolutely is. And there's also a signal that comes from the CPU, and it goes to the video display processor that basically says, hey, I'm accessing RAM, don't do anything with the RAM right now. And that signal is getting to the 6847 as well. So the question I have to put out there to everyone who had one of these machines, is this static normal for animation, or is this just something that's faulty with my machine? I tried to look online for recordings from actual hardware, and all I could really find is emulator footage on YouTube. And obviously that stuff's not going to emulate the static. I also looked around in the documentation. I didn't really see anything about this, but I don't see any problems with the signals that are passing between the CPU and the video display processor. Not to mention, we know the interrupt is picking up the 50 Hertz perfectly because the dead test ROM displayed 50 Hertz, and it uses that signal going into the interrupt on the CPU to count cycles and figure out your display refresh rate. Let's try the next game. I think this one is called Space RAM. Now I've noticed that some stuff loads with a B colon, other things loads with a T colon. And I wonder if B is for binary, T is for text. And these .vz files that you download, there was a little utility that I found for Windows that takes that VZ file and creates a WAV file. And I'm just playing the WAV file in VLC. And that's all you really need to do to load software onto this computer. But there we go, this loaded. Joystick yes or no. Of course we say no. Space RAM. So I is for instructions, S is for start. And I know the keys already because I played this earlier. This does have sound. It's quiet. But you go around this maze. Ah, see, I'm trying to turn. Look at the static. I just don't get it. I don't get why the static is so bad. But it's not a bad game. And the weird thing is the speed is inconsistent. Sometimes it speeds up, sometimes it slows down. Not sure what's going on exactly. Again, I kind of wonder if this was like written for 60 Hertz machines and maybe it's having issues running at 50 Hertz, but I mean, most of these computers were sold in 50 hertz markets as far as I'm aware. Let's see, look how quick it's going now. There we go, I finished the level. So with that little speaker in there, it's still pretty quiet. Obviously, I'd need to put an amplifier in there if I wanted to get louder sound. There's no static when there's no animation, but as soon as the game starts, it's not great. Oh, see, I'm pushing up. You just kind of have to hold up. There we go. Oh yeah, if I shoot the yellow guy, then I blow up. That's kind of an interesting thing. And they call it frame 2 for level 2. So I don't want to shoot the yellow guy. He's like my doppelganger in a way, but I have to wait till the very end. Oh, go away. I have to shoot him at the very end. And if I hit anything, of course, that kills me. And I think I ran out of time. I didn't notice that there's a clock at the top. I mean, you know what? This game's not bad. And if this is all I had back in the day, I think I would have been okay with this. I mean, it's not great. And it makes VIC-20 games seem... Oh no, that finished the level. Okay, so I don't have to shoot the other yellow thing. I guess frame 3. Yeah, I mean, VIC-20 games, they seem a lot better than this. But, you know, let me know what you think. And I didn't do much research on, like, what is the best game for this system. But, man, it's very sluggish the way it responds. Oh, okay. So that's Space Ram with an R. Okay, there's another game here called Star Blaster. Now, incidentally, while we wait for this to load, I did see there was one graphical demo made for this, and it looked pretty cool. There was, like, scrollers and some cool stuff was happening. It doesn't work on this machine for some reason. When I load it, it loads the title screen, and then that's it. Again, I watched a demo of it running, and it gets past the title screen, and it seems to load intermittently. It's pretty cool what they did is they have a WAV file you play on your phone. One channel is music to play through some speakers, and the other channel is the data for the computer. And it seems to load data and then pause for a bit, load some more data. So as it's a graphical demo, it does some effects, then it loads some more data from tape, and does some more stuff. It seemed pretty neat. It does not work on this machine other than loading the title screen. And I'll just show you that it can load the title screen. It gets that far, but that's it. All right, loading error. Yeah, I've had trouble loading this particular program. Could try again, I guess. I don't know what to do to make it work. It did run once, but maybe I have to turn up the volume. I mean, the volume's maxed out, and these WAV files were generated all by the same program. So it doesn't really make sense that some of them work perfectly and other ones not. Okay, all right, I give up on that one. Let's try this demo. Here comes the demo. If it were, oh, there it goes. So 5-finger punch. I think the demo is called 2018 AD. So it loads this, and the screen scrolls a little, and then that's it. And we can hear the music actually if I turn up the speaker. This is the audio channel you're supposed to hear through your speakers. This is not coming from the computer. So yeah, kind of cool, but I think it's supposed to do stuff at this point more than what's actually happening here. And the final thing I want to talk about is the shimmering you can see for the color video. If we take away the color, the shimmering is gone. That is specifically on the color decoding, which is that little circuit board on this machine. The video display chip on this outputs component video output, so a luma signal plus 2 color signals, and the board that's in here converts that into a regular chroma signal, which would be good for YC, aka S-video, but then there's a circuit on the motherboard that just combines them together, and it gives us the composite video we're looking at here. I am much more experienced at looking at NTSC color, and this shimmering that's going on here seems like it's a couple clocks that are somehow out of phase. The main video chip is running at 3.78 megahertz, and then the color carrier color board is running at 4.43, which is the PAL color frequency. I'm not sure if those are interacting with each other and that's what's causing this. And I don't know if all the machines were like that or there is a fault on this board. It seems to give good color otherwise. It's just the shimmer is kind of ugly. But I think in the end, this machine does feel like it's filled with tons of compromises, and I wouldn't be surprised if this shimmery color was one of them. So there we have it. That's the VZ200 done. This thing is fully operational and working. I think it's working pretty much as well as it's ever gonna work. And the fact is, it's got 34 kilobytes of RAM in here now. So I'm super curious to know if anyone has ever done that ROM mod before. It's just a single chip soldered on top of the EPROM with a total of, I think, 5 baud wires. I just reused that gate that was down on the board here, and there we go. There could still be some problems with expansion peripherals, of course, because that RAM is hard-coded into the machine. Possibly I could have installed a little toggle switch on the case that would have just disabled the chip select line to the chip, and that would just take it out of circuit while you were using an expansion module and put this thing back to 2K. But I'm assuming most expansion modules expect you to have a 6K of main motherboard RAM along with the 2K of video RAM, and they weren't even really designed for this 2K system like this one is here. So if you enjoyed this very long and thorough troubleshooting video, I'd appreciate a thumbs up. I had a ton of fun working on this thing. Even though the computer feels very compromised, it was still neat just because it's such a weird and rare machine that I'd never worked on before. A huge thanks to Tommy at Arctic Retro for sending this in the first place. There's a link down below to his channel and of course the original video where I talked about this thing. I think it was Super Mini Mail Call 22. That was a long time ago. I think I'm up to 99 right now. And as you just watched over the last 2 parts, this thing, even though it's simple, was not easy to fix, and that's because there were no bad chips at all on this machine. It was entirely a physical problem on the motherboard. The low quality PCB, along with that scuff on the back under the ROMs, caused all of our issues. I think the one on the CPU with the address line that went to the video ROM, or video RAM that is, that caused that page error. I think that was probably my fault from when I socketed the CPU, but all that stuff that happened under the ROMs, that was already there. And I really have to wonder, was that there from when this machine was brand new? Which might explain why it really looks completely unused. So there you go. I hope you learned something by watching this. And if you liked it, I appreciate a thumbs up. If you didn't, you know what to do. Thanks to my supporters, names are going off the side of the screen. You can become a supporter at the links down below. There's YouTube membership, Patreon, all that kind of stuff. Subscribe if you haven't already. And I guess that's going to be that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.